Welcome to today's session, where we uncover one of the silent killers in programming, global variables. They may look convenient, but in reality, they're ticking time bombs for embedded systems and multi-threaded applications. Global variables can trigger race conditions and unpredictable errors that bring entire systems crashing down. In this video, we'll break down why relying on them is dangerous, how they sabotage performance, and what smarter ways you should use to keep your code stable, efficient, and future-proof. Let's dive into the world of safe programming practices and learn how to protect our systems from these hidden threats. But are globals always evil? Not exactly. There are a few controlled situations where they can actually make sense. One example is communication between an interrupt service routine and the main program loop. In this case, a global variable acts as a simple bridge, one writer, one reader, and the risks of race conditions are minimized. It's a clean way to pass data without heavy synchronization. Another exception comes in performance-critical systems where memory is extremely tight. Globals can reduce stack usage and CPU overhead, helping the system run more efficiently. But this only works if you enforce strict discipline and keep access patterns crystal clear. Without that control, the same problems we discussed earlier will creep back in. So while globals are usually system killers, in these rare cases they can be a practical tool, if handled with care and precision. Now let's look at why globals can be so dangerous in real-time systems. The first big issue is non-atomic access, also called torn writes. Imagine a 32-bit variable being updated in multiple steps. If an interrupt fires in the middle of that update, the data gets split, leaving behind a corrupted value. That's how a clean number like 0x12345678 can suddenly turn into garbage like 0x1234AB78. The second risk is data inconsistency caused by race conditions. Picture this: thread A reads a value, but before it can finish updating, thread B jumps in and changes it. When thread A resumes, it's working with an outdated copy, and the final result is wrong. This overlap, called read-modify-write conflict, leads to lost updates and unpredictable behavior. Together, torn writes and race conditions show why managing shared state in embedded RTOS development is so tricky. Without atomic operations and proper synchronization, your system can collapse under these hidden errors. So how do we defend against torn writes and race conditions? The answer lies in mandatory best practices. The first tool is mutexes and locks. By enforcing single-thread access, we make sure only one task touches the shared data at a time, eliminating conflicts. Next, atomic operations. These allow a read or write to happen in one indivisible step. No interruptions, no partial updates, just clean, reliable data handling. And finally, the gold standard, message queues. Instead of multiple threads fighting over shared variables, we pass data through queues. This way, tasks exchange information safely without ever touching the same memory directly. Together, these practices aim for a shared nothing architecture. That's the safest design principle. Each task owns its data, and communication happens through controlled channels. It's the foundation of reliable embedded system development. So, what's the final verdict on global variables? The developer consensus is clear. Treat them with extreme caution. In multi-threaded systems, globals are viewed with deep skepticism because they open the door to race conditions, unpredictable states, and those dreaded Heisenbergs, errors that appear and disappear without warning. In embedded RTOS development, they are one of the biggest sources of system failure when threads interact unsafely. That's why the safest path forward is to aim for a shared nothing architecture. Each task should own its data, and communication should happen through controlled mechanisms like message queues, locks, or atomic operations. This is how we build systems that are reliable, predictable, and resilient. In case you like the video, please show your support, like, share, and subscribe to the channel Core Tech Education for more content like this. And if you'd like me to create a video on your selected topics, share your ideas in the comment section. Thank you. Thanks a lot for watching it.